Hi, welcome to the third training session of the MK UWB kit. My name is Yanis Aguilar and I will be your host in this session. This session focuses on the development of UWB applications using the MK UWB SDK. It is divided in 4 modules. We'll start with an introduction to the MK UWB SDK, the typical architecture of an UWB application, its main components, and how to find them in the material included in the UWB kit for mobile knowledge. Still in the first module, we'll give an overview of the MK UWB library, what it does, and which APIs and methods it provides. After that, in the second module, we'll take a step-by-step look at how to implement a simple use case for SR150 using the UWB Shield tool provided with the kit. Finally, in the third module, we will complete the use case by implementing the SR040 counterpart using the SR040 tag in the kit. So let's get started with an overview of the MK UWB SDK. The MK UWB SDK is a set of software tools, libraries and examples that enables you to start developing UWB applications and products that use NXP Trimension, SR040 and SR150 UWB chips. A typical application based in the MK UWB SDK has an application layer that implements the business logic specific to the use case or to the product. Below that, the MK UWB library is responsible for enabling access to UWB functionality. It provides a high-level API to common UWB services. The library relies on the NXP UWB middleware, which manages the communication with the UWB chip. Finally, a board-specific layer is needed to connect the application and the UWB library with the underlying hardware. The SDK is finally built for a specific platform or board that includes one of the NXP Trimension products. It includes some working examples that run on the UWB Shield 2 and the SR040 UWB tag. It is also delivered with tools for interfacing with UWB devices and for visualizing UWB data in computers and in Android smartphones. The MK UWB SDK is included in the USB stick that is shipped with the kit. The folder software MK UWB SDK binaries contains precompiled binary images for the hardware platform supported by the SDK out of the box. This is the SR040 UWB tag and the UWB Shield 2, either connected to an SR150 or to an SR040 module. Images for some legacy boards are also included in the SDK. These are the UWB Shield and the UWB tag SR150. These are antecessor boards of the ones in the UWB kit. They are no longer distributed under regular conditions, so if access to any of them is needed, please contact Mobile Knowledge. The source folder contains a zip package with the source code of the SDK and project files to import it in MCU Expresso, which provides full access to updating, editing and developing with the SDK. To follow up with the rest of the explanations in this training session, you will need to unzip the SDK onto your destination folder. We will now see the main components of this architecture in detail. The central component of any application based in the MK UWB SDK is the MK UWB library. It is delivered as a set of precompiled library binaries and its corresponding C header files. The library provides access to common functionality in UWB applications, like for example, initializing and terminating UWB and also Bluetooth Low Energy hardware, detecting nearby devices over Bluetooth Low Energy and launching UWB sessions when supported devices are detected, receiving real-time distance and angle of arrival notifications that can be handled by the application, and it also provides some functionality for white and blacklisting devices, so that the application can select which devices it wants to enable UWB with and which not. The SDK, as delivered with the kit, provides access to the MK UWB Lite version, which is a limited version of the library. Access to the complete version of the library requires a specific license agreement with Mobile Knowledge. If you have unzipped the SDK, the folder libs under MK UWB Library contains the precompiled library files. The light version of the library built for SR040, the light version of the library built for SR150, and also 2 extra dummy files with empty libraries that serve as placeholders for the full versions of the library when available. Also, the includes folder contains the header files with all the definitions, methods, and types that your application will use to access the library. Exactly the same structure shows in MCU Expresso after you import the SDK into it. Let's continue now with the UWB middleware. The MK UWB library relies on the NXP UWB middleware to access the UWB chip. The UWB middleware from NXP provides a lower abstraction level C API to UWB functionality, and it implements the UCI, or the UWB controller interface, which is the protocol to communicate with the chip. UWB applications based on the MK UWB SDK will commonly access UWB services through the MK UWB library. However, the application or any other software component may still access the middleware directly and bypass the library if necessary. There are actually 2 different UWB middleware packages from NXP, one for SR040 and another one for SR150 chips, both included in the MK UWB SDK. The code of both middleware versions is fully available, and as mentioned, middleware APIs may be accessed from anywhere in the application if necessary. Again, the same structure is followed in the software project in MCU Expresso. The build configuration in MCU Expresso selects the right middleware for the UWB chip on the target board, and the resulting software image is always built against only one of the 2 middlewares. Both the UWB middleware by NXP and the UWB library from Mobile Knowledge are hardware agnostic. This means that they need an additional layer to connect them to the underlying hardware and to give them access to GPIOs, communication interfaces, services provided by the RTOs, and the like. This is the role of the adaptation layer or port. As of today, the MK UWB SDK is delivered with working ports for QN9090 microcontrollers on the boards included with the kit, and for the legacy boards that we saw just some minutes ago. All these ports share most of the code, though some parts are board specific to adapt to the different pin mappings and to some other minor differences across the platforms. A port for an RF52840 by Nordic Semiconductors will be shortly available and will be included as part of the SDK. The source code for all the supported boards is available under the Platforms folder in the SDK. Also, all the necessary files to import and build the projects are also provided and are loaded when imported into MCU Expresso. As usual, the same structure of folders is loaded in the MCU Expresso project, with one folder for each supported board. Of course, platforms not supported by MCU Expresso but still included in the kit will not be loaded here. There is also a common folder with the code shared across the many hardware platforms, including some HAL API implementations, which we will see later in detail later on. Also, for each platform, the top-level folder contains some generic files required to support the board, and a folder called HAL IMPL that contains the port of the NXP UWB middleware for that platform. Additionally, other resources specific to the MCU or to the board are also loaded into the project. For example, in this case, the QN9090 SDK. The only remaining item in the software architecture is the application layer. The application layer is in charge of implementing the logic specific to the use case. It usually accesses UWB services through calls to the MK UWB library, and it may also use any other libraries or software components. The SDK includes 2 examples of such application layers. The first example is the anchor, which implements a device controlled by an external host, typically a PC, but it could also be another microcontroller or another board. The host sends commands to the anchor and receives responses and data from ultra-wideband sessions. The anchor is the application that runs on the ultra-wideband shield 2 as delivered with the ultra-wideband kit. The second example of an application layer is the tag. It implements a standalone device with no external host and with limited functionality. This is the application that runs on the ultra-wideband tag SR040 boards that are delivered with the kit. The source files that implement the tag and the anchor applications are delivered in their corresponding folders in the SDK. The common folder contains some files with definitions and methods used in both applications. Again, the folder structure in the MCU Expressor project maps that of the folders in the SDK. The build configuration takes charge of selecting only the right files and folders for the build and excluding the rest. We've seen the main components on a typical application based on the MK UWB SDK. Now we'll see in detail the MK UWB library and how the application and the rest of the components interface with it. The MK UWB library exposes 4 interfaces that define how it is accessed from the application and how the library accesses other components in the software architecture. Interfaces can be divided into 2 main categories. On one hand, methods and APIs that are implemented by the library. These are methods that other components will call to trigger some behavior in the library. In this category, there is the MK UWB Library API and the HAL Hooks API. The first one, the MK UWB Library API, is the main API exposed by the library and gives access to ultra-wideband functionality and also to configure the library behavior. The second one, the HAL Hooks API, is a set of functions that are implemented by the library and called typically from the SDK port and platform layers to report events that have to be handled by the library, typically BLE events and similar events. On the other hand, we have the methods and APIs that need to be implemented by the application developer and that are called by the library, the HAL API and the MK UWB App Handle Hook. The HAL API gathers all the methods that the library uses to access the hardware and other functionality in the microprocessor. For example, to access Bluetooth Low Energy services or to toggle the pins that control the power supply of the ultra-wideband chip, if any are available. Finally, the library calls the method MK UWB App Handler to signal or to forward events that may need handling by the application. Typically, this is data from ultra-wideband sessions with other devices. We'll now go briefly through all the methods defined by the different API categories in the library. If further details are needed for any specific method, please check the SDK guide which is delivered with the kit. As we've just seen, the MK UWB Library API is the main API that the application calls to trigger some action or to change some behavior in the library. Before calling any other methods, MK UWB init must be called by the application so that the library starts up and initializes any resources needed. On the other hand, MK UWB uninit terminates the library and releases all the resources. No other API should be called after terminating the library, except of course MK UWB init, which will start the library again. The ultra-wideband library uses Bluetooth Low Energy to detect other devices in range, and eventually it starts a ultra-wideband session with them if the right conditions are met. This mechanism can be started and halted by the application by calling MK UWB Start Detection and MK UWB Stop Detection. MK UWB Start Detection takes some arguments to configure the behavior of the detection, like what kind of devices might be detected. These are only SR040 devices, only SR150 devices, or any of them. Also, whitelist and blacklists may be also configured as detection policy, so that either only the devices in a whitelist or all the devices except those in the blacklist are selectable for ultra-wideband sessions. White and blacklisting can be also disabled, so the library will not apply any of these policies. After detection has started, Calling MK UWB stop detection will stop it, and it will also stop any ongoing UWB sessions. Black lists and white lists work with lists of MAC addresses that are used later on to filter out or select devices for UWB sessions. The library provides methods to update these lists. For example, for white lists, the application can add a specific MAC address to the list by calling MK UWB whitelist add. It can also add a whole range of addresses by calling MK UWB whitelist add range. Similarly, addresses and ranges of addresses can be removed by calling MK UWB whitelist remove and MK UWB whitelist remove range, and the list can be cleared and reset to an empty state by calling MK UWB whitelist clear. An identical set of methods is also available to update the blacklist. Please note that on the light version of the library, some of the methods for managing whitelists are not available, and the blacklists are not available at all. Also, whitelists and blacklists only have effect on the detection if the corresponding policy is selected when calling MK UWB start detection. The application can also update and read the value of some other configurations by calling MK UWB setConfig and MK UWB readConfig. This includes configurations such as the UWB channel that will be used for UWB sessions, the UWB ranging interval, and others. As these configurations have an impact on ultra-wideband sessions, they may be updated only when detection is not active. The light version of the library may restrict the access to some of these configurations. Please check the SDK documentation in case of doubt. We'll now see a couple more of APIs that do not belong to any of the categories that we've just gone through. While detection is active, the library also stores the latest ultra-wideband data for ongoing ultra-wideband sessions. This data can be retrieved by the application by calling MK read ranging data. This way, the application may ignore any ultra-wideband notifications or even disable them, and call MK read ranging data to read the latest available ultra-wideband data only when needed. Finally, MK UWB get platform info fills the structure with platform information such as the version of the library, the version of the NXP UWB middleware, and other useful data that identifies the platform the library is running on. All the APIs we've seen so far are called by the application to produce some action or to change the behavior of the library. Instead, MK UWB app handler is a method that the library calls to report an event that may need handling by the application layer. For example, that a supported device has been detected over Bluetooth Low Energy, or that ultra-wideband data is available for an ongoing session. This is not implemented in the library, but instead needs to be coded in the application layer. A typical implementation will handle the data linked to the event and react according to the specific requirements of the product or the use case under development. We've seen how the application layer communicates with the library. We'll now follow with the APIs that are meant to connect the library with the hardware it runs on. As we have already covered, the HAL API is the set of methods that must be provided to the library so that it can access the hardware and other services that depend on the hardware platform, such as RTO services or Bluetooth Low Energy. The first group of such methods provides the library with access to BLE functionality, as we'll see now. The library calls MKBLE init to make sure that BLE hardware and any other resources are initialized. This may be ignored, for example, if BLE is initialized somewhere else in the application code. On the other hand, MKBLE uninit signals that the library will use the BLE functionality no more, meaning that BLE may be terminated and any resources associated with it may be released. MKBLE advertising start and MKBLE advertising stop are called to start and stop advertising, and similarly MKBLE scan start and MKBLE scan stop are called by the library to start and stop Bluetooth Low Energy scan. Finally, the library may call MK BLE set advertising data to configure the data in the advertising packet. The next three APIs deal with sleep or low power modes in the microcontroller or the processor running the library. MKLP init is called by the library to trigger the initialization of the low power modes and any resources associated with it. MKLP enter signals that the library allows entering low power mode, while MKLP exit is called by the library to request leaving low power mode. The implementation of these three methods depends largely on the power mode supported by the host and how they are managed. Typically, the library will allow entering low power mode when ultra-wideband is not active, and it will request leaving it when access to the communication bus with the ultra-wideband chip is needed. The implementation of these three functions may be omitted if the hardware doesn't support or doesn't need to support any low power modes. If so, the functions may be implemented with empty stubs. Link to the low power APIs we have just covered. The library may request powering up or powering down the ultra-wideband chip. It does that by calling MK ultra-wideband power on and MK ultra-wideband power off. Depending on the board design, this might trigger enabling or disabling any PMU that may control the power supply of the chip. In case the power supply of the ultra-wideband chip can't be controlled by the host, these methods may be left empty. Of course, this may have an impact on power consumption. The platform port must also implement a set of methods to access common RTO services. This covers methods for creating and managing threads or tasks, message queues, semaphores, mutexes, timers, and also management of dynamic memory. You can check the SDK guide for the complete list of OSAL APIs that must be implemented in the library port. The port implementation also has to implement some utility methods. This includes methods for handling debug messages from the library, providing random numbers when needed, and also handling critical errors that the library detected and could not recover from. The application also has to configure if the library will behave as a tag or as an anchor. This is done by calling MK ultra-wideband set platform hardware, and it has an impact on how the detection mechanism works and how the library behaves upon detecting other ultra-wideband devices. This is why it must be called before ever calling MK ultra-wideband start detection. The last group of APIs are called by the port to report some events that need to be handled by the ultra-wideband library. For example, to report that BLE advertising has stopped or started, or that BLE scan has stopped or started. Also, the library port must report devices detected in a BLE scan and forward the data in the advertising packet to the library. We have covered all the APIs that the library exposes to communicate with it. These are the entry points and interfaces that any application using the library will use to access ultra-wideband functionality. By implementing the HAL APIs and calling the right hooks, the MK ultra-wideband SDK can be ported to other microcontrollers and boards where the MK ultra-wideband library can be used. Now we'll move on and see the requirements that such a microcontroller must meet. First, the MK UWB library is built for Cortex-M4. Thus, only microcontrollers based on Cortex-M4 are selectable for running the library. Still, other architectures may be supported in the future. If you need to extend the support to other microcontroller families, please contact Mobile Knowledge. Of course, hardware must be equipped with try-mentioned SR150 or SR040 ultra-wideband chips from NXP, and also SPI bus, and all the necessary physical connections must be available for the microcontroller to communicate with the ultra-wideband chip and control it. Bluetooth Low Energy 5.0 or 4.2 must be available too. BLE may be supported by the same host that the ultra-wideband library runs on, or it may be supported by another hardware part, for example a dedicated BLE module assembled in the PCB. In this case, it is responsibility of the library port to route all the BLE functionality to the right hardware component. The ultra-wideband library also needs access to RTOs, with common functionalities such as tasks or threads, queues, semaphores and the like. Also, access to dynamic memory must be supported, typically through malloc and free and similar methods. This is usually implemented by the RTOs, implementations of the C standard library, or even third-party libraries. The microcontroller will also need some sort of flash or non-volatile memory to store the software image and to execute from it, and volatile RAM memory to store temporary data, execution state and context. In terms of flash, about 340 kilobytes of memory are needed, of which 100 kilobytes are used by the library and the rest by the NXP middleware. Regarding RAM memory, about 31 kilobytes of RAM are needed. These figures correspond to ports based on the SR150 chip and the SR150 middleware from NXP. Yet, similar figures can be expected for SR040 ports. In any case, these numbers do not take into account other requirements such as the BLE stack, RTOs, and other libraries, which will probably need extra flash and RAM memory. Let's now do a quick recap on what we've covered so far. We've seen what an application that uses the MK UWB Library and the MK UWB SDK looks like, along with its typical software architecture and main components when it comes to ultra-wideband. We have also seen what APIs the ultra-wideband library provides, how to interface with them, and what is needed to port the SDK to another platform. We'll soon jump to modules 2 and 3 of this training session, which cover the practical contents and in which we will show how to develop for SR150 and for SR040 chips. But before we move on, let's spend some time and introduce a real-world use case in which ultra-wideband may be used. We will use this use case, or maybe a simplified version of it, later on to showcase the development for the ultra-wideband chips. Let's imagine that we get a request from a customer. They want to deploy an access control system with ultra-wideband. This will include two different types of devices. First, ultra-wideband locks. These are devices equipped with SR150, connected to the power grid, and which control a door lock. Also, the ultra-wideband locks hold a list of devices that may access the door and restrict the access to anyone else. We will also have access tags equipped with SR040 and powered with a small console. Tags may be distributed to people so that they can access the doors controlled by the ultra-wideband locks, provided they have the right permissions for it. We also have some requirements from our customer. First, the ultra-wideband lock will unlock the door only if it detects an access tag with access permission and within a distance of 2 meters. Also, the ultra-wideband lock will lock the door back after 5 seconds, regardless if there is anyone around or if any other tags are detected nearby. By the way, this doesn't sound very safe, and you may want to review this requirement in a real-world use case. Anyway, for the sake of simplicity, we will take it as is. The third requirement is that the ultra-wideband lock must provide some mechanism to load the addresses of the access tags with access permissions. And finally, the access tag will blink a green LED if within 2 meters of an ultra-wideband lock for which the user has access permission. As you have probably figured out, we will use the ultra-wideband shield 2 delivered in the ultra-wideband kit to implement the ultra-wideband lock, and the SR040 ultra-wideband tag to implement the access tag. We will also build 2 applications, one for each device, that will meet the customer requirements. Also, we will extend and use the PC shell, a tool that is also delivered with the kit, to monitor the unlock events and to load the addresses of the devices with access permission.